So let's start. So this is centre of mass, and centre of mass is important because things revolve around their centre of mass, and we tend to take things like gravity, we tend to take from the centre of mass of one object to the centre of mass of another object. So sometimes it's valuable for us to work out where the centre of mass is, and there's several different ways, there's several different situations. There's basically a situation where we have everything on just one axis. And we say, okay, well, there's our first point, and there's our second point, and we can figure it out, say, for the x-axis or the y-axis or the z-axis. Then the next level of complexity is we have things in three-dimensional space. So we do the same scenario with IJK notation. And then the third is where we have a distributed mass. So it could be a solid, could be a asteroid, or it could be something like that. We're not going to do something three-dimensional. We're going to do a two-dimensional sheet. And to keep the math accessible, we're going to do a triangular three-dimensional sheet, although we could just as easily do some other mathematical function. I'll show you how to do that. It follows on from our preceding use of calculus in other sections. We're following the same pattern, actually, of just we're going to make the calculus just a little bit more complicated step by step as we go through. So it's the next step on our journey as far as using calculus in physics is concerned. The key thing is, if you look at these equations, they're all kind of similar. There's always, on the top, there's always the individual mass and the individual mass's position. And we're going to summarize those. And then we divide it by the sum of all the masses. And if we're talking in terms of x-axis, our positions are defined in terms of an x-axis. And if we're talking in terms of three-dimensional space, our positions are defined in terms of three-dimensional space. And even down here, we have all the masses added together, which is the total mass. And we have each individual mass multiplied by its position. So it's the same formula. It's just three versions of the same formula. So I don't learn three formulas. I learn, one formula, and then I change it based on the circumstances. Okay. So it's going to be the mass times the position over the mass. That's the pattern. So let's do this one. I'll do this one with you. So a 2 kilogram mass is located at position x equals 5. So here we have 2 kilograms, and this is 5 meters. And a 3 kilogram mass is located at position x equals 4. So this is 3 kilograms, and this is 4 meters. And so we say, where is the center of mass? Well, we know it's going to be between the 3 mass and the 2 mass. So we know it's going to be between 4 meters and 5 meters. And if you were to make a guess, would it be more towards the 4 meters or more towards the 5 meters? It's more towards the 4 because the 4 is heavier. It's got more mass. So we have a rough idea of where it should be. But let's use this expression. So we're going to say x center of mass is equal to the sum, and it's the mass times its position along the, let's call it x, its position along the x-axis, over the sum of all the masses. These are i's. We tend to, when we're doing iterative things, we call them I, meaning I is 1, I is 2, I is 3, I is 4. If there's 5 things, I is 5 eventually. So x center of mass is equal to, now we're just working out this sum on top. So I pick one of these guys. I'm going to say, well, it's the mass, which is 3, times the position, which is 4, plus the mass, which is 2, times the position, which is 5, over the mass, which is 3, plus the mass, which is 2. So this would be 12 plus 10 over 5, which would be 22 over 5, which would be 4.4 meters. Well, and really we said it was going to be between 4 and 5 meters, and it is, and we said it would be closer to the 4 than the 5, which it is. So it makes it's a sensible answer. Cool? So one-dimensional. Don't worry about the axis. X, Y, Z makes absolutely no difference. You just do your expression and you get it. Are you okay on that?
Do the I stand for initial?
No. As I said, the I's are just for iterative. So if the first mass is 1, the I is 1. If the second mass is, you're calling it 2, the I is 2. It's just a numbering system. Okay? But it tends to come up a lot. 2 kilogram mass is located. Let's draw the diagram together. And notice, I'm not making any attempt to be realistic. I'm not doing my XYZ axis and trying to map out exactly where it is. I could do. You could do. It's just practice. But I don't need it. All I need to do is visualize 3 masses surrounding a point of origin. So I'm going to go my first mass, and this is 2. And this is going to be 3I plus 4J plus 2K meters. And then my second mass is 3 kilograms. And it's minus 2I plus 3J minus 2K meters.
Why is this diagram different from the last one?
Because in the last one, it was on the x-axis. And this one is using IJK notation. So I don't want to draw them in a line if they're not in a line. I'm not going to be realistic and try and get them exactly where they should be, but I am going to try and represent to myself the fact that they're occupying more than one-dimensional space. Okay. And I want to find my center of mass. And my center of mass on my diagram is going to be somewhere between the two of them. It's going to be my center of mass. And because I'm working in 3 dimensions, the tradition is I use an R rather than an X or a Y or a Z. I just say, oh, it's this vector. And so what I do is I write down my X center of mass is equal to the sum of MIRI over the sum of MI. And I say, well, based on that, my R center of mass is equal to the sum of XI, that was XI. I gave the game away. RI over the sum of MI. So I'm trying to reinforce,
What's the difference?
I'm trying to reinforce to myself that there's not really a difference between these two, although in the book they're written down as 2 different equations. Just one is only on one axis and the other one is in 3-dimensional space.
Does it matter which one you use for this question?
You better use the IJK vectors for it, but the symbols, I can live with either symbol.
Like the X, not R's.
I can live with that.
Okay.
Okay, but you know, if you just recognize that it's a 3-dimensional vector, then you can just put the R down, you know. So then I say, well, let's do this. So I'm going to basically do an IJK like I did before. And the steps are going to be, I'm going to have my, let's do it, M1R1. And then I'm going to have my M2R2. I'm going to have my sum. And then I'm going to have my sum divided by M1 plus M2. It's the same mechanism, isn't it? Can you do that for me, please? Just write it out and do it, and then pick your answer. And plug in your answers. And I'll pause here. Okay, we're back. And if we look at this, what did people say? Mainly E. Let's just check that out. So I have M1 times R1. So let me get my pen. That's going to be 6. That's going to be 8. Listen up, please. Listen up, please. And the next is going to be 3 times that, minus 6. 9. And minus 6. Add them together. 0. 17 minus 2. And then divide by your 2 masses, which is 5. So 0, that's going to be 3.4. And that's going to be minus 0.4. So I think my answer is 0I plus 3.4J minus 0.4K meters. Is that one of the choices? Cool. Cool. So not bad. Don't let IJKs put you off. I think if you do this grid, it's just sums. If you're trying to do it in your head, if you're not practicing doing the grid, if you try and just lay it out on your page, I think people make lots of slips. So I think the grid really helps. This next one I'm going to do, and then you're going to do. So I'm going to do it, and then you're going to do it. So this next one is about basically a 4 meter. Oh, I forgot about this one. A 4 meter long rod is positioned with one end on the origin and the other end at plus 4 meters. So that's 0 meters, and that's 4 meters. And it says the rod is uniform. That means constant density, constant width, linear mass density is nice and steady, nice and constant. It's like like a flagpole, uniform rod. The mass equals 8 kilograms. And using the method of calculus, as shown in physics class, show that the location of the center of mass is at plus 2 meters. Well, yeah, we know that. It's a uniform rod. So, what am I doing here? I'm just learning the technique. Okay, well, if that's what we got to do, that's what we got to do. So we say, what was that last equation? Well, the first equation was x center of mass is equal to the sum of mi xi over the sum of mi. And then we could also say that, well, our center of mass was equal to the sum of mi ri, where ri is a vector, of course, over the sum of mi. And so by analogy, my expectation is that for a distributed mass, and this is a mass that has so many atoms, you couldn't possibly add together all the atoms and do this. So it's like a cloud of matter. For a distributed mass, we say that, well, let's see if we can figure it out. We're going to say that my x center of mass is going to equal, well, it's going to be the integral of r dm over all of the masses, which is the total mass.
So big M means
Total mass, yeah, total mass. Is that the equation I wrote down before? I had 1 over m, I think, integral, yeah? And it was r dm. Now, it's not mdr. It's rdm. And I can't justify to you why that's not the other way around, but it's not.
Shouldn't be RCM equals.
It doesn't. The little letter doesn't matter. It's just you know what it stands for. So it doesn't. I can't justify you why it's this way around, and that I think is the hard bit. It's like you got to remember. I hate things you got to remember, but you got to remember that it's rdm, not mdr. Because if it's mdr, it's a much easier problem, but it's not. And I can honestly tell you, let's just rewrite this in a slightly different form, 1 over m integral of rdm. I have no idea how to do that problem, because I don't know how you integrate r's with respect to dm's. Don't know how you do it. Let me just go back. I want to just look back. 1 second. It is, yes. Okay. I don't know how to do it. So I got to find some way of converting the dm into a dr. Okay. Well, if I look here, there's what my dm physically represents. And here's what my dr. dr is the width. And if I make a thicker slice, I get more mass in the slice. So there's a direct relationship between the mass in the slice and the width of the slice. So there is a relationship between dm, the mass, and dr, the slice width. So let's figure that out.
Which
So,
one's the DR and
well, it's the bottom with the 2 arrows, that's the dr, and the top is saying the dm. It's the same thing, it's just the width of it versus the mass of it. Okay?
So the dm's the mass?
Yeah, dm is the little bit of mass. D meaning little bit. So dr is the little bit of the of the distance, and dm is the little bit of the mass. So we say, well, let's see if we can do this. dm is equal to, well, put my physics hat on, and I can say, well, dm, the little bit of mass, would be the little bit of width times the linear mass density. Now, frankly, I could have said the volume mass density, in which case I'd have to figure out a volume for this slice. And I could, it's uniform depth and uniform height, so I can do that. But there's no need because it's uniform. So we can think of it in terms of linear mass density. And I say, well, hold on, my dm is equal to dr. My mass density, density is what units for density? It's going to be
grams per centimeter.
upstairs in chemistry maybe, but what's it going to be down here? Okay.
Got busted, Orgo.
Physics, kilograms per cubic meter. Yeah, kilograms per cubic meter. So, kilograms mass, cubic meter, some kind of dimensional length thing. Yeah, it's a volume in that case. This is a linear mass density. So that's going to be mass over the length. Oh, okay. I can say, yeah, my linear charge density is the total mass over the total length. Doesn't that make sense? That gives me grams per meter in this case. Kilograms per meter in this case. So, I'm going to leave those as letters just for a minute or two. What I've learned over the years is by not substituting in numbers earlier, I can catch mistakes more often. And sometimes things cancel. I don't even need to know what they are. I know when I began, I wanted to put numbers in straight away because I felt uncomfortable with letters. But I would encourage you, do what is comfortable to you to get the right answer. But I would encourage you to try and just leave the letters in a bit longer and see what happens. So what we say is, okay, so that says that my centre of mass position is equal to 1 over m times the integral of r. And instead of this dm, I'm going to put down dr m over L. Now, the way we do integrations is we take out everything that's
There's going to be 1 over L.
just hold on. The way we do these things is we take out everything that's constant. So we go x centre of mass is equal to 1 over m. This mass, of course, doesn't change. And, of course, that L doesn't change. And that's the integral of r dr. And I know how to do that. This is going to be equal to, well, my masses cancel. So this is 1 over L times the increase the power by 1, put it under the denominator, r squared over 2. And I need to do my limits. Well, I'm measuring from this end, and the first slice is at 0. And I'm going to that end, and the last slice is at L, if you like. Let's leave it with letters even longer.
You drop the almo before?
I'm sorry?
You drop the almo down?
Oh, I'm sorry. Yeah.
Thank you.
Yeah, thanks. Sorry about that. So then we say, okay, this is not so bad. I say, let's come down here. Let's find my pen again. Come on, pen. There you go. So I come down here and I say, okay, then my x centre of mass is equal to 1 over L times, and this is going to be L squared over 2 minus 0 squared over 2, which equals, as I said, I'm going to leave that in terms of L. So then that's going to be equal L squared over 2L, which equals L over 2. And what is L? L is 4, which equals 4 over 2, which equals 2 meters. So my numerical answer for this question is 2 meters. My, if you like, my algebraic answer for this is L over 2. We know that intuitively. But we've done it using the method of calculus. So if you like, we proved mathematically that, well, we proved using physics and math that that's where the centre of mass should be. Okay?
I'm still not getting where after you integrated 1 over L, and then it was R squared over 2 from 0 to 4.
No, 0 to L. I said I left it in terms of L.
To L.
And then later on I substituted in the 4.
Like a 4 from okay.
I was going to write a 4 and then I changed it to an L because I thought I've got a good idea here.
And also if they ask you for a different size rod too, you would still know.
So now that raises an issue, which is if I say in an exam using the method of calculus as shown in class, this is what I want. I have got to see this bit here. I've got to see that starting equation. I've got to see that starting equation. I've got to see your justification for going from dm into a dr. I've got to see you do the calculus. I've got to see you substitute in what you need to substitute in. So although you know the answer in the end, and you're going to work out these equations, when I say using the method of calculus as shown in class, that's what I want. I want this process.
The diagram is not needed though?
I'm sorry?
The diagram is not needed?
You're not needed? Oh, I can't what you're saying. I'm sorry.
Even.
Not like you have to draw the diagram as well as the calculus part?
Jump into it.
So I'm your coach. What do I say about diagrams?
Draw 'em.
You know? So
I got you, coach.
good. Okay. So let's try to remember that throughout the rest of the season. Okay. So 5 meter long rod is positioned with one end at 4. Oh, now does that old joke about I show you the easiest example and then all the things you do are harder?
Yeah.
Which is true. I want you to have a go at this, but I'm not starting at the 0. My rod is starting at the 4 meter and the 9 meter. But if you just follow that same methodology, it'll all fall out. So have a go at it. And I would substitute, I wouldn't do that last little bit where you leave L for as long as possible. I'd substitute in your limits and just solve it using your limits. So I'm going to draw it. So this is 5 meters. And then plus 9 meters. And M equals 6 kilograms. And
No,
there's,
it's from 4 to 9, sorry.
I'm sorry?
From 4
Oh,
to 9.
it's 4 to 9.
Yeah, it's a 5 meter long.
Yeah, thanks.
You're good.
Thanks.
Just I don't want to catch you before you get too
I know,
deep
yeah,
into it.
I'd be dead. So let's resume. So most people are saying E. I did a little bit of work while we were off tape, so let's just talk over that. And I want to show you this last little bit, because it's the last little bit that catches people. So we have a similar diagram. It's not starting at the origin. That was just a special case last time. We're starting off at some distance, and we basically write down our expression. I reminded myself what it was, and it was 1 over m, integral of r dm. I don't know how to do that kind of integral, so I need to change my dm into a dr, so it's dm equals dr, which is the little slice width times the linear density. And so dm is equal to dr times the total mass over the total length of the rod. And then I substitute that in, so I go my centre of mass is equal to 1 over m integral of r, and then rather than dm I put down dr m over l, and then I say, well, okay, let's take out all the constant things, and my m comes out, but it cancels with the m underneath, and my l is coming out, so it's 1 over l times the integral of r dr, and I know how to do that integral, so it's going to be 1 over l r squared over 2, because you increase the power by 1, you put it in the denominator. Now, at this point, I suppose if I was been a purist, I would get you to put letters in for the, I'd get you to put letters in for the limits, but in truth, it's a lot easier if we just actually use numbers at this point. So I'm going to change this. So let's look and see what these letters stand for. One is the nearest slice, and one is the furthest slice. So this is the nearest slice to where I'm measuring from. And so I need that distance as one of my limits, and that's going to be +4. And then the other one is my farthest slice, which is way down here. And so that's my limit on that side, and that is +9. So as in the first example, we had L for the length and L for one of the limits. That was a special case. This is a general case where we have the limit goes, well, between 9 and it goes down as far as 4.
So this has definitive.
So this would work under all circumstances. You could have done it last time. And maybe I should not do the special case. But. So then you say, well, x centre of mass is going to equal 1 over L. So I look at my diagram and I say, well, my length is going to be 9 minus 4, which is 5. And then I have 9 squared over 2 minus 4 squared over 2, which equals 1 over 5. And that's 81 over 2 minus 16 over 2. So x centre of mass is going to equal 1 over 5. And 81 minus 16 is 71, 65. So that's going to be 65 over 2, which equals 65 over 10. And if I've done that right, that's 6.5 meters. So the position is at 6.5 meters. And I can do a quick calculation and say 2.5 plus, because it's going to be in the middle of the rod again, isn't it? So 2.5, which is the distance to the middle of the rod, 2.5 plus 4 is 6.5. So again, this makes sense.
Because it's a uniform rod.
Because it's a uniform rod.
If it wasn't uniform, like maybe if you had a little extra metal down here.
I got to do some extra math.
Yeah.
And that's what we're going to do next. Okay. Cool? Okay? Questions?
For the question before, we could have just substituted the 4 for the L and still would have been easy.
Yeah, as I said, yeah, you can always substitute the numbers in. That's what I always used to do. But as I've got older, what I've found is that when you put numbers in it and you make a slip, you can't see the slip so easily. So I've learned as a strategy to try and hold off on the numbers for a while.
Just substitute last. Huh?
Substitute if you can last. But this is a case where I would not have left it in algebraic beyond where I did. And it's just you've got to feel your comfort in that. You know, I understand entirely putting numbers in early. What I'm saying is that as you get more confident and you get more experience, just see that as a strategy to try and help you. Do you notice something about both of these answers, about the mass?
It's center.
Well, no, about the numerical value of the mass.
Oh, it's directly in the middle.
Does not matter. The mass does not matter. So I can give you this question without stating the mass. And that will upset people. If people are used to doing it piecemeal, they'll say, well, let's see, I've got to work out my density. Well, density is mass over the length. I can't work out my density. So then they're stuck. And again, that's a trick. You see it a lot in the back of the book problems on you know, things like AP tests and stuff like that. Because it's trying to sort out, are people thinking in sentences or are people thinking in little phrases? You know, density is, boom. Well, no. The density is part of a sentence. Yes.
Would we have an example change in the DM?
Do you mean a non-linear
Correct.
rod?
Yeah.
So next we're going to do, because we're going to do a triangle. The ultimate non-linear thing. Now, notice I'm working on an axis. In the last two questions I've worked on an axis, and I'm going to continue working on an axis. So I would ask you, where along the x-axis is the center of mass? I could also, as a different question, say, where along the y-axis is the center of mass? And you could figure it out. But we're not going to do generic, IJK vectors in this kind of thing. That's certainly not going to happen. This is going to be very formulaic, and it's going to be kind of like this. So, okay. This says, a 5 kilogram sheet of metal is positioned as shown. Using the method of calculus as shown in physics class, show that the x-coordinate, so the x-axis position for the centre of mass is +2. So my actually centre of mass is going to be somewhere like that. That's really where my centre of mass is going to be. But I want to find out that x position there. That's what I'm looking at. That's the thing. So I need to just, having said that, I need to just get the eraser out and remove that so that we can keep it clean. So then I'm going to turn around and say, well, hold on. Sorry. So I'm going to turn around and say, well, hold on, my x centre of mass is equal to the sum of mi xi over the sum of mi. And my r centre of mass is equal to the sum of my mi ri over the m centre of mass. And that then gives me that my x centre of mass is equal to 1 over m integral, and it was r dm, wasn't it? Is it r dm?
Yeah,
I'm doing it the right way around. That's the thing I worry about with this. That's the thing I worry about.
X, mine's X, and then my
Can you
right.
just write the line
He's done.
equation we're going to use?
Yeah, okay. What were we saying?
Can you just write the line equation we're going to use?
Yeah, but I'll tell you what, I'll know these equations really well because I've written them down so many times. Never miss an opportunity to write a basic equation down, because by the time the test comes, you don't even have to learn it the night before. You know it. I swear, if you do your homework, writing down the equations and not just putting down numbers, by the time the test comes, you know the equations. I can't guarantee it for you, but I swear it's going to make life so much easier. If you just put numbers down, you're never going to practice the equations, and then in the test, you might not remember the equations. So
All about the approach, right?
it's about constant training. It's about you don't do the Olympics by starting training the night before. And what we do is just as hard as what they do. So practice, practice, practice. Okay, I have no idea how to do this. Again, I'm back where I started from, and I have to figure this out. And this is going to be a little bit more interesting. So I'm going to make a thick slice so I can really decide on this. And this is going to be my dm, and it's going to have a certain thickness dr. So there's my physics bit. I'm saying, hey, I do integration by doing slices. And I say, well, if I could just figure out an expression for dm in terms of dr for any slice, then it's going to work. And so it's going to be, well, my dm is going to equal. Now, I got to recognize that this is an area.
Trapezoid?
Well, I'm going to cheat.
Yeah,
This is an area. And so I need to recognize that this is my little bit of area times my area density. Not my linear density. That won't work in this case. I'm going to do my little bit of area times my area density. And then I say, well, my dm is equal to I need an expression for my little bit of area. I know the base of it is dr. I need to invent something for the height. Let's call it height. And I don't care about the fact that there's two slightly different heights. I'm going to make my slices so thin that h left and h right are going to be basically the same thing. So I'm going to cheat and say, pretend it's a rectangle. It's so thin, it's like a rectangle.
works for me.
And then I'm going to say my area density is the total mass over the area. So, if you like, the total area, the area of the triangle. So I say, well, my dm is equal to, let's do that bit first. dr, I'm still going to deal with h. And I'm still going to have mass. And then what's the area of a triangle?
1/2
Base times height.
base times height.
So let's call this base big X. And let's call this height big Y. So this is going to be a half big X times big Y. Okay? I know the value of x, I know the value of y, I know the value for m. This will work, except that if I pick a different slice, I have a different h. That's my only problem. I just don't have a constant value for h. So h depends upon my r position. There's my r position. That's how far I am along. So I say, let's sort that out next. I say dm is equal to dr.
Where does the h come from?
I am defined it. I said I'm going to call that h.
What exactly is the form of
Area
area density?
density is the total mass over the total area. Okay?
I'll work it
So then the next thing I have is I want to find an expression that expresses h in terms of r. Because h is not a constant, and the only variable I can have is an r variable. So I look over here and I go, oh, this is like y is equal to mx plus b. That's just an equation for that line, isn't it? So h is equal to the slope. Yeah, I should call it slope, shouldn't I? Because m's been used. Slope times r plus, and what does it go through? 0. So h is equal to, what is the slope of this? Rise over run? Do I have letters for that? What's it going to be? Big Y over big X times R.
Is that slope r plus
Yeah.
0?
The slope times R plus 0 equals H. Everybody see where that comes from? This is a straight line. So it means that I can express it using the straight line graph equation, which is the y coordinate is equal to the slope times the x coordinate plus b, which is the y-axis intercept. Which is 0. So my h at any given r is h is equal to the slope of the actual line times the r, which is the x-axis coordinate, plus the y-axis intercept, which is 0. Then I look at my diagram and I go, well, my x, my slope is the rise over the run, which is my total y over my total x, or my big Y over my big X. So I take this guy and I bring it down here instead of my H. So I go big Y
Not all of it.
over big X times R times M over 1/2 X times Y.
Y's cancel.
So things cancel. Let's have a look and let's do a different colored pen so we can see this really nicely. Let's do red. So my Y's cancel. And that's it, isn't it?
Can you make the half a 2 on top?
I can. So let's go back to black. So, boom, boom, boom. So let's have a look. I'm not going to change things around. I'm just going to keep the same order. dr times r times m. Let's bring that half and make it a 2 on top over x, which equals, now let's rearrange.
Wouldn't be x squared?
X squared, thank you. So let's rearrange things. So that's going to be 2m r dr over x squared. So I had 2 steps in this substitution. The first was figuring out the area density bit, and then the second thing was figuring out the variable height bit. And so then I turn around and say, well, okay, let's get on with it then. So then we say my centre of mass x coordinate is equal to 1 over m integral of r dm, which equals 1 over m the integral of r. And rather than dm, I'm going to put down 2m r dr over x squared. So my x centre of mass is equal to 1 over m. Let's bring out all the common stuff. 2m, not common, constant stuff, over x squared. Took my 2m out, took my x squared out, left my 1 over m out. Integral of r squared dr. Let's do a little bit of cancellation there. The m's go away again. So then x centre of mass is equal to 2 over x squared, oops, square brackets, r cubed over 3,
Is the bound 0 to 3?
and the boundary, I'm going to be kind of, because it's on the axis, because it's starting on the x-axis, I can do this trick where I go, well, it's just going to be 0 to big X. So I say x centre of mass is equal to 2 over x squared, and then I'm going to go x cubed over 3 minus 0 cubed over 3. So my x centre of mass is equal to, and that's going to be 2/3 x. So x centre of mass is equal to 2/3 of 3, which equals 2 meters. Yeah. 2/3 times x, which is 2 over 3 times 3. And that makes sense. It's not going to be at 1.5 because it's a non-uniform object. Most of the mass is to the right rather than the left. So I expect it to be closer to the 3 rather than the 1.5. And it is. It's closer.
We did all this work for 2?
So what do you think? It's doable, isn't it? And it's, if you think of it from a physics point of view, it just takes you through it step by step. First of all, you say, well, I can't integrate R in terms of dm, so I've got to change my dm. So I start using the area density. And then I realize, oh, my h depends on R as well, so I've got to substitute in an equation for that. And so I can go on. Yes?
Before you integrated, where did you get the r squared from?
Let's have a look. Which line are we on?
The one where you crossed out the m.
Oh, because I have an R here, and I have an R there. Yeah. And people, because they're separate, people sometimes miss them. That's why I do very little in my head. I'm not teaching you. I'm letting you look over my shoulder. I mean, this is how I would do it. If I rushed it, man, I would make more mistakes. So this is not kind of me kind of like going, oh, I better go slow for them. This is me trying to get the answer right. Okay.
If we would have used the trapezoid instead of the area density, would it came out right as well?
Try it. You go home and try it, and then see if it helps you or it makes it harder, or if you get a different answer. You will get a different answer. Because in principle, when you bring those two slices, thinner and thinner and thinner, it looks less and less. The slope becomes less significant for the two heights. The two heights become very similar. And in the limit, as delta x goes to 0, the two heights are the same. So I don't think there's a need for that. Okay. Have a go. Nothing like trying it now.